We are finishing off section 9.2 sequences, and we're going to start by looking at the geometric sequence. So to give you an idea of what that is, some of you may remember, I'm going to write out a sequence here and see if you can figure out the next few terms. Let me write another one, then you can pause the video and see if you can figure them out. Whoopsies. It's not what I wanted. Let's do this. All right, go ahead and pause, try these, and we'll come back and I'll explain how to do them. All right, hopefully you were successful. The pattern you should see, to go from here to here, you multiply by 3. To move from here to here, you multiply by 3. To move here to here, you multiply by 3. Continuing that pattern, you should have 81, 243. And what's 243 times 3? I'm going to grab my calculator because I'm not that smart. 243 times 3, 729. All right, so this next one, did you figure the pattern out? Well, here is the secret. You multiply by 2/3. So what happens, that cancels and leaves 27, and that cancels and leaves 8. Then we continue multiplying by 2. Let's try that again. By 2/3. The 3 cancels the 27, leaves 9. The 2 and 8, you divide both and you get 4. And that's how we get 9/4. Then you multiply by 2/3 again. That leaves you 3 on top and 2 on the bottom. Then you multiply by 2/3 again. And everything cancels. And you have 1. Then you multiply by 2/3 again, and you get 2/3. So that's the pattern there. Let me erase all this extracurricular. Whoa, I didn't mean to do that. Let's undo that. Yeah. Can I do this without losing everything? Nice. Oopsies. Yeah, so you see the pattern. So what is a geometric sequence? It's when the next term is figured out by multiplying by the same number over and over. So you just keep on multiplying by the same number. So that number is called a common ratio, R. So R is the common ratio, and that's what you're multiplying each time. And then the secret for finding the common ratio, R, you take any term and divide it by its previous term to find your R. So in our first example, I will underline as blue. You take 3 and divide it by the previous one, and you get 3. Then we'll do the next two. 9 divided by 3 is 3. Then the next two. 27 divided by 9 is 3. That has to work through the whole thing to be geometric. And then the second one, which was not as obvious, we would do the same thing. Let me underline this with the fuchsia-ish color. So how do you find your common ratio, and how do you figure out if it's geometric? We divide. I'm dyslexic, that's backwards. You divide 27/8 by the previous term, which is 81/16, but you multiply by the reciprocal, and that goes in that twice. 9 goes into that 3 times, and that's whoa. I'm sorry, my brain is glitching here. Let me back up. So 9 goes into this 3 times and goes into that 4 times, and that reduces. Whoa, am I messing up here? 27/8 divided by 81/16 times 16 over 81. Okay, we got 2. And oh, wow, I am just so lame-o right now. So 27 goes into 81 3 times, and you get 2/3. Then you test the next pair, and I'm not going to do this for a lot of them, but you take any term, divide it by the previous term, which is you multiply by the reciprocal. 4 goes in 8 twice, 9 goes in 27 3 times, you get 2/3. And so you see the pattern, that's how you find what you multiply by. So that is a geometric sequence. Now, what are we going to do with this? I don't want you to see that yet. So I'm going to give you a couple of sequences, and we're going to look at these and see what happens. So the first one, my sequence a sub n is going to be 0.75 n. So we're going to find the first few terms, a sub 1, a sub 2, a sub 3, a sub 4. Now the first one's easy. Let's plug a 1 in there, and everyone knows that's 0.75. Now, if you plug a 2 in here, it's going to be 0.75 times 0.75. So I'm going to do that in my fancy schmancy calculator. I think I am. And I get 0.56, and I should do it in a pen, 0.5625. Now, how do I get my next term? Well, I plug a 3 here. So that's going to be 3 of these multiplied. But this is already 2 of them, so I multiply that by 0.75. And when I do that, I get 0.421875. Now, the last one is a sub 4. That means that's the 4th power, but that's already 3 of them. So I'm just going to multiply that by 0.75. So the pattern fits. You keep multiplying by the common ratio. And when I do that, I get 0.31640,625. And we're going to look at that pattern and see if we can learn anything from that. Let me go ahead and do another one. Actually, you can try this if you wish. My a sub n formula will be 1.5 to the n power. So we'll find a sub 1, a sub 2, a sub 3, a sub 4. The first one's easy. First power is just going to be 1.5. You can figure out the rest if you want and pause, and I'll just keep going. So the next one, you're going to have a 2 there, because you're looking for a sub 2. It's just going to be that times another 1.5. So what do we get? .5 times 1.5, 2.25. I knew that. I just didn't want to be embarrassed and say it and it come out wrong. Okay, so next we want a sub 3. So that's going to be cubed. That's already squared, so we're going to multiply that by 1.5. So we'll do that, and we get 3.375. And again, to get the next term, we already have 3 there. We're going to multiply by 1.5 again to get the next one. And so the last one will be 5.0625. And here's what you should notice. What's happening to the numbers here as we move down? They're getting smaller and smaller and smaller because we're multiplying by a number less than 1. So therefore it's going to keep decreasing. And eventually you should see that it should go to 0. Here, what's happening? They keep getting bigger and bigger and bigger because you're multiplying by more than 1. So each number is going to get larger. This is going to go to infinity. So this is what you need to get. If you have a geometric sequence, a common ratio raised to the nth power, now when's it going to equal? Okay, check this out. This limit, so that's going to be the limit of the sequence. What the terms approach as n goes to infinity, it's going to approach 0 if your absolute value of r is less than 1. Because remember, if you multiply by something less than 1, it's going to get smaller and smaller and smaller. So it should make sense. Now, it'll equal 1 if your r is 1. If your r is 1, you're starting with 1. It's going to be 1 to the n, right? Well, 1 to the 1 is 1. 1 squared is 1. 1 cubed is 1. It's always 1 because this is 1 times 1. And so if your r is 1, your sum, or the limit of your infinite sequence will be 1. And if your absolute value r is less than 1 or r is bigger than 1, now understand what r less than 1 means. Here's an example of r less than 1 or negative 1, 1.01. That's less than 1, negative 1.1. So you should realize when you're less than negative 1, your magnitude of your numbers is bigger than 1. Okay? So basically, if your r is bigger than 1 in magnitude, as you keep multiplying, they're going to get bigger and bigger and bigger without bound. So you're going to have a geometric sequence where the limit of the sequence does not exist. So that's all that chart is saying for you. All right? And the last thing that we're going to go over is growth rates of sequences. So what is happening here? This makes life easier. You're going to have a new way to find limits, and it's based on growth rates. So let me first look at this chart and see what this chart is showing us. So let me draw a graph that represents each of these functions. All right, so first we're going to look at ln. So here's what's happening. ln, you should all know it looks like this. That's ln of x. And I could put x's for all these n's. That might make more sense to you. That n might throw some of you off. So that's ln of x. That's the slowest growth rate of the functions we're looking at because it flattens out. It's even slower than a line. A line has a higher growth rate than ln. So that's what's happening with that one. The next one, which I made a mess out of, which is x to the p power, that's just like a polynomial, x squared, x cubed. So the example for that I will do in a different color for you. X to the p. Here's an example of x to the p, and that's y equals x to the first. Here's another example of x to the p. That's y equals x squared. So clearly what's happening, if you have a polynomial function, x to the p power, that's bigger or a faster growth rate than ln of x. That's growing faster. That's growing slow. Now this one I won't really look at. It's just a combination of these two, so we'll ignore that. But take a look at that. All it's saying is if you have a higher exponent, it's going to grow faster. Obviously, x squared grows faster than x to the first. And so if your exponent is larger, you know it has a higher growth rate. All right? So that's what we're looking at there. I will do the next one in a new color. Let's see what looks pretty. I like green. So b to the n. So that's some number raised to a power. So it could be 2 to the x would be an example. 3 to the x would be an example. That's exponential growth. E to the x is an example. So exponents have exponential growth, like e to the x. And you have to know that has a higher growth rate than, and I erased it, I don't know what I did, than a polynomial type function. And then we're left with, I'm not even going to graph these next two, and these are pretty easy to remember. I will do this in this color. A factorial grows faster than exponential, and the last one on the list is like x to the x power. A number raised to its own power has the fastest growth rate. So you need to know that order of those growth rates. And what's significant about this? And here is where life gets better. If you take a limit of a function divided by a function, okay? If this has a smaller growth rate than this, that's growing faster, that's growing slower, that's what it's saying, your limit's going to be 0. Because the top one's growing slower than the bottom. Pretty easy, eh? And this one says if the top one has a higher growth rate than the bottom, then the limit's infinity. So this opens up a new way of finding limits that makes things easier by looking at growth rates. All right, that's your lesson for the day. And that's it. I don't know why I'm keeping talking. You guys can shut this off because it's over.